Welcome learners, this is Black Slides once again. We meet now to revise a 2024 mock paper, Physics Paper 1 from DESHA. This paper was set by what is called the DESHA Examinations Board. I went through this paper several times and I discovered very useful questions in it, which I would like us to share now. All right. So if you are watching this video lesson on our YouTube channel, once again subscribe to Black Slides, hitting the notification bell in the process, so that every time we upload something new, you get notification. But if what you want is to join us in our main classroom, don't hesitate to send us a text message to this number here. We'll be very much excited to share with you the joining process. The joining process. So welcome learners. Invite your friends to join us. This is the platform to revise, the platform to learn, and the platform to be engaged academically. Remember, we are offering also holiday lessons up to the first week of September, and after that we are going to continue teaching normally up to next year when you are writing the 2027 MSCE exams. So without wasting your precious time, let us get down to the business of the day, which is to revise this paper, which I found very useful. Right. So welcome to section A. Remember that section A contains 10 questions and gives us a total of 70 marks to score. So question number 1 is saying explain how parallax errors, I'm sure it's referring to parallax errors in a measurement, can be minimized. Recall that parallax errors are errors originating from poor positioning of the eye with respect to the measurement scale. If your line of sight is not in line with the scale from which you are taking a reading, you are bound to record a wrong value or erroneous value due to poor positioning of your eye or eyes during observation when you're taking a reading. So if you don't position your eye correctly with respect to the scale, your measurement is going to be erroneous, and that is going to affect the quality of your measurement. Welcome learners. So the question is saying explain how we can correct that, how we can minimize, not correct but minimize, reduce the occurrence of such errors. You do this by simply taking a reading. Read the measurements with your eyes directly perpendicular. Perpendicular means right angle So your line of sight must be perpendicular or at right angles to the scale. Let's say you are using a ruler. Your line of sight must not be oblique to the line, to the scale where you're taking the measurement from. So the angle between the scale and the line of sight should be 90 degrees. That way you are bound to get a better result, a better reading than when your line of sight is oblique to the surface. So you're saying, in order to minimize such errors, simply read measurements with your eyes directly perpendicular to the scale. Or if you are using glassware such as burettes or measuring cylinder, your line of sight must target the bottom of the meniscus. Or if you are doing a Hooke's law experiment where you are guided by a pointer on the ruler, the scale, you should position your eye in such a way that the line of sight is perpendicular to the scale where the pointer lies. So by saying this, you have 1 mark. Welcome to question number 1B. Figure below shows a micrometer screw gauge and a vernier caliper. We are asked to give the values shown by the 2 instruments. What's this? What's the reading here? And what's the reading here? How do you determine the readings? So remember that a micrometer screw gauge, this is the micrometer screw gauge. How do we know that? The micrometer screw gauge has what is called the sleeve scale. This is called a sleeve scale. And then you have a thimble scale. That's how we know that this is a micrometer screw gauge. Also, we know that this is a vernier caliper because it has the main scale and the vernier scale down here. So let's look at each of these instruments and determine the readings. So for the micrometer screw gauge, first you read the main scale or the sleeve scale from the point or division just close to the thimble scale. So the reading must come from here. So the reading here is 6.5. 6.5 millimeters, and you add that to the reading here, which is 21, this one. But remember to multiply the 21 by the least count for the micrometer screw gauge, which is 0.01, and then you add the 2. So you take the reading there, that's 6.5 millimeters. That's the division mark just before the thimble here. The thimble scale is 21. This is 21 here. If this is 20 and that's 22, that means this one here is 21. So you multiply that by 0.01, which is 0.21. Then the final reading will be the sleeve scale, which is 6.5, plus the thimble scale, which is 0.21. So you get a total of 6.71 millimeters. So the reading there is 6.71 millimeters. Okay. Let's look at this one, the vernier caliper. The vernier caliper, when you're taking a reading from a vernier caliper, first of all, consider the reading to the left of the 0 of the vernier scale. So the reading here is 4. The mark before the 0 mark is 4. Count this. Excuse me, this is 3 and this is 4. Okay, so this must be 3.4. This is 3.4. That's 3 centimeters and 4 millimeters. That makes it 3.4. So you put that aside. That's called main scale reading. And then you go on the vernier scale. Look at the lines on the vernier scale, which correctly, exactly aligns or lines up with another line on the vernier, on the main scale. So such a point is right here, this one. You can notice that this line here lines up with that one up there. And this is happening at 4. 1, 2, 3, 4. So you take that 4 multiplied by 0.01, which is the least count for the vernier caliper, and then add the 2. So you're saying the main scale is taken from the 0 of vernier must to the left hand side. We're saying the 0 of vernier sits after 3.4. So this is 3.4, this point. That's 3 centimeters and 4 millimeters, which is 0.4. All right. So count the vernier lines, and you find that line 4, this line 4 is right here. You start counting 1, 2, 3, 4. So line 4 lines up perfectly with the main scale line right here, where the two are facing each other side by side. So the vernier value there for the vernier value scale reading will be 4, which we get from here, multiplied by the least count, which is 0.01, to give us 0.04 centimeters. So the total reading therefore is going to be 3.4, which we got here, plus 0.04, which gives us 0.44 centimeters. If you have not got this right, kindly send us a message to our WhatsApp number. We'll be glad to re-explain, to make even a short video for you to explain this again, to make it simpler for you. That's what we are here to do. Welcome, learners. Question number 2. Explain how the density of water changes as temperature increases from 0 degrees to 4 degrees Celsius. So explain how. Recall that water behaves in an unusual way, which is called anomalous expansion, of course anomalous contraction as well. When you cool water from 4 degrees Celsius down to 0 degrees Celsius, its volume increases. In other words, water expands when you cool it from 4 to 0. Contrary to the behavior of other substances. For other substances, you will expect expansion when you are moving from a higher temperature to a lower temperature. You will expect some substances to contract, actually to decrease in its volume and size when cooled from 4 to 0 degrees Celsius. But water behaves the other way around. When you cool water from 4 to 0, water expands. In other words, its volume increases, although its mass remains the same. Okay, so for this one, we are moving from 0 to 4. So we are asked to explain how the density of water changes as temperature increases from 0, which is lower than 4. So what happens is that the mass of the water remains the same, by the way, assuming there's no transferring of matter between the container and its surroundings. So mass stays constant or the same as temperature rises from 0 degrees to 4 degrees Celsius. But what changes is its volume. So its volume decreases. You know that density is mass divided by volume. Okay, so when the volume decreases, it means that the quotient, when you divide mass by volume, such decreasing volume, you get a bigger value, which is density. So we are saying mass stays constant as temperature rises from 0 degrees to 4 degrees Celsius. So you'd say that up to that point, 1 mark, volume decreases, hence density increases. So we are saying as the temperature of the water increases from 0 to 4, its density decreases. Why? Because volume, its density increases. Why? Because volume decreases. So mass stays constant as temperature rises from 0 to 4, but volume decreases, hence density increases. That's how it should be. So by saying these points, you have 2 marks here. Briefly describe how a fish survives. How fish survive in frozen waters. Again, this is an application of the anomalous behavior of water. So pay attention to the number of marks. This is 3 marks. Alright, so briefly describe how fish survive. How do fish survive in frozen water? You'd expect fish to die there if the temperatures become frozen or very, very low. But nature provides it that the fish will survive even under such conditions. So how? Okay. Alright, so water is actually most dense at 4 degrees Celsius. In other words, we are saying water is heaviest at this temperature. So because of that, it sinks to the bottom. Remember that high density objects sink in water. So water which is at 4 degrees Celsius is most dense. Therefore, it's going to sink to the bottom of the water. And the ice, which is less dense, remember, ice is less dense than liquid water. So ice which is less dense will float to the top. In so doing, it acts as an insulator. So the liquid water below the ice stays at 4 degrees Celsius. So the fish will live there and survive. So the 3 marks are for the 3 points that we have here. Welcome, learners. Question number 3, differentiate between distance and displacement. This question tests your understanding of vectors and scalar quantities. So the difference that the examiners are looking for, which is 2 marks, must say something about distance being just the length of path, and that it is a scalar quantity, and the displacement is a straight line, and it has direction, therefore it's a vector. So distance is a scalar quantity and the displacement is a vector quantity. That's the key difference between the two. So we are saying distance is the total length of the path traveled, and it's a scalar quantity. That's 1 mark. While displacement is the straight line distance from start to finish, including direction, and it is a vector quantity. So the key difference here is the fact that distance is a scalar quantity, while displacement is a vector quantity. A truck delivering supplies to a construction site is late with delivery. The truck covered the first 10,000 meters of the trip in 600 seconds. How much time does the truck have to cover the remaining 4,000 meters? So that is average velocity is 20 meters per second. Okay, so here we have to be a little bit careful. What are these things? This is distance, and that's time for the first part. So the first part consists of 10,000 meters covered in 600 seconds. So the question is, how much time does the truck have to cover the remaining 4,000 meters? So that is average speed. So average velocity is 20 meters per second. Alright, so first of all, find the total distance that the truck has to cover. So the total distance is 10,000 plus 4,000, that's 14,000. And the total time needed. Remember, time is distance divided by average speed. So the total time needed is the total distance, which is 14,000, divided by the average speed or average velocity, this one, which is 700 seconds. But we are told that it has already used up 600 seconds. So to find the remaining time, just subtract the 700 seconds minus the one that it has already spent covering 10,000 meters. So that will be 700 minus 600, which is 100 seconds, which is basically a minute or so. If you divide this by 60, you find it's 1 point something minutes. That means it's quite short. Or maybe the truck is traveling at highest velocity, as you can see here. Welcome, learners. This is Black Slides Online Secondary School, your platform. This is your online school while you're at home. A body is thrown vertically upwards with initial velocity of 20 meters per second. Given that the gravitational acceleration is 10 meters per second square, this should be per second square, not 2s. Alright, make that correction. This must be s to the power 2. Work out the maximum height reached by the body above the starting point. Work out the maximum height. In other words, we are asked to calculate the vertical distance. So check that we are told the initial velocity, and we are also given the value of g is 10. So work out the maximum height of the vertical distance reached by the body above the starting point. Right, so this requires you to use an appropriate Sauvat equations, because we are given g, which is the same as acceleration, and this is u. So using those two values, we have to work out the maximum height, which is s when you are looking at Sauvat equations. Yeah. So one thing that you need to remember all the time is that when an object is thrown upwards vertically, when it reaches its maximum height, the final velocity there is going to be 0, because the body will not, before it returns to the ground where it was thrown from, it's going to stop for just a short while, momentarily. So its velocity there is going to be 0. When you throw any object, let's say you are throwing a ball up, before it returns back to your hand to catch it, it will stop in the air for just a very small time. So that is final velocity, which is 0. So initial velocity is that, the starting velocity is 20 meters per second, and its final velocity in the air is going to be 0. So we are, for that reason, going to need this guy here, the equation, one of the equations of motion, or one of the Sauvat equations, as they are sometimes called. It's going to be v squared equals to u squared minus 2as, which is going to be 2gh. So take note that the h is replacing the s in the Sauvat equations, and the g is replacing a, the acceleration. So substituting the given values at maximum height, v is going to be 0. So it just puts 0 there, square it. And the u is 20, we are told, this one here. So squaring 20, and then multiply, subtract 2 minus 10, which is the value of g, multiplied by h. So the only variable to worry about is h, which is the one they're asking us to find. So solving for h, in this case, will give us h equals to 20 meters. So that's how high the body will fly to the maximum height. Welcome, learners. Once again, you don't hesitate to ask questions if we have left you behind on this one. Question number 4. Differentiate between ohmic conductors and non-ohmic conductors. This is from electricity. All right. Recall that ohmic conductors are materials which obey Ohm's law, for which resistance is constant and current is directly proportional to voltage. That's what Ohm's law states. So we are saying ohmic conductors are simply those that obey Ohm's law. Okay, an example is copper wire. Copper wire doesn't heat up that much, and its resistance can remain constant for a long time. And when you plot a graph of current versus a voltage for such a conductor, you produce a straight line through the origin. Okay. Well, non-ohmic conductors are those which don't obey Ohm's law. And the resistance through such conductors, the resistance of such conductors, it changes with current or voltage. They are the ones that heat up like a filament bulb. Does not obey Ohm's law. Therefore, it's non-ohmic conductor. Figure 2 below is a circuit diagram. So just let's check the network of resistors. We have resistors that are connected to each other. We have these 2 ohms resistor connected to this parallel circuit, and then the whole band is connected to another resistor here, 5 ohms, which is also connected to another parallel circuit like that. We have 1, 2, 3, 4, 5, 6 resistors, 4 of which are in parallel arrangement. Like here we have these 2 resistors which are in parallel arrangement. Here as well, they are also connected in parallel arrangement. So we are asked to calculate the equivalent resistance in the circuit. So equivalent resistance here means the total resistance. That's what it means. Sometimes the question will say calculate the effective resistance. Still, they're asking you for the same thing, to calculate the total resistance. So the hint here is that you should treat the parallel circuit separately in the first place. So add up 3 ohms to 4 ohms in parallel, and also add up 2 ohms to 5 ohms in parallel. What you find here, you add to this one, which is in series. You also add the result you get there, and add this one. That will give you the total resistance. So we are saying, let's call this parallel circuit 1. So when you have 2 resistors that are in parallel arrangement, their sum is simply found by multiplying the 2 and dividing by their sum. We call that product over sum. So you take 3 times 4, which is 12, and take 3 plus 4, which is 7. Then 12 divided by 7 is 1.7, this one. Just keep it for now. You do the same for this one. You take 2 multiplied by 5, which is 10, and divide by 2 plus 5, which is 7. 10 divided by 7 is 1.4. Once you do that, you're almost done. So you take the 1.4 you find here, add it to 1.7, and then add it to 2, and then to 5. That will give you a total resistance of 10.1. It's as simple as that. List 2 factors that affect the efficiency of a transformer. When you are doing electricity, especially transmission, power transmission, you are told that the transformer is not 100% perfect. A transformer is not 100% efficient. There are sources of energy loss, so that its efficiency is not going to be 100%. All right. So some of the causes of energy losses or power losses in a transformer include resistance of the coils. Remember that a transformer is made up of a coil around the core, So the resistance of the wire from which the turns are made can result in losses, heating effects. So one factor is resistance, heating in coils. Another one is eddy currents, very, very small currents which are lost in the iron core of the transformer can lead to power losses. Another one is hysteresis loss and flux linkage. Please take note, not linkage, but leakage, not linkage, no any here. State the two assumptions made in the kinetic theory of gases. So first of all, you must recall what the kinetic theory of gases states. The kinetic theory of gases states that gases are made up of very, very tiny particles which move randomly in all directions, and the speed of their movement increases with the increasing thermodynamic temperature. That's what the kinetic theory states. So for the theory to hold, or to make sense, there are some assumptions that need to be put straight. Okay, so the assumptions upon which this is made are that gas molecules are far apart. We assume that they don't come together, they don't stick to each other. Right? So they occupy a volume compared negligible volume compared to volume of the container. Okay, so the particles are far apart, and also there are no intermolecular forces between the gas molecules, meaning that the gas molecules don't stick to each other, such that the collisions between the particles are perfectly elastic, meaning both their momentum and kinetic energy is conserved. Explain the importance of each of the following features in a liquid in a glass thermometer. The constriction, I think the question is with reference to the clinical thermometer, because it is the clinical thermometer that has constriction. So the use of the constriction in the thermometer, in a clinical thermometer, is to prevent liquid from flowing back quickly, so its reading stays steady after use. So the constriction prevents the flow back of the liquid in it, so that you should be able to take a reading after use. It has a thin capillary tube with uniform cross section. Alright, so the thin capillary tube makes the liquid level move most visibly to give accurate, evenly spaced readings. So in other words, is for us to be able to take a reading. So I'm assuming it is quite thick. Assuming that the capillary is thick, it would be, for some reason, be difficult for us to take readings from it. It also makes it more sensitive for taking readings. 1 mark. A gas occupies a volume of 2 cubic meters when its pressure is 1140 millimeters of mercury and its temperature is 27 degrees Celsius. What volume would it occupy at standard temperature and pressure? That's at 0 degrees Celsius and 760 millimeters of mercury. This is the standard temperature and pressure. So we are asked to calculate volume. So this calls for what is called the combined gas law. Since we are moving from one pressure and volume as well as temperature to another pressure, volume, and temperature. Alright, so for the initial conditions, the pressure is 1140 and the volume is 2, while the temperature is 27. Alright, so we use this equation, which is called the combined gas law, used especially when the parameters such as pressure, volume, and temperature are important. So the law says that the pressure of the initial pressure of the gas multiplied by the initial volume of the gas divided by its temperature is equal to the final pressure multiplied by the final volume divided by the final temperature. And also recall that the temperatures should be in absolute terms, meaning that it should be in Kelvins. So you change the temperatures into Kelvin. So in this case, the 27 degrees Celsius will become, you simply add simply add 273 to 27 to give you 300 kelvins. So this temperature here is 300 kelvins, and the 0 degrees Celsius is 273. Just add 273 to get the temperature to in kelvins. Alright, so we are given the initial pressure like that with the volume given like that, and the temperature is we just converted to kelvins, and we are given the final pressure as well as the final temperature. So what's the final volume? So just have from this equation just to make V2 the subject of the formula. So if you carefully make V2 the subject of the formula and substitute accordingly, then the volume is going to be 2.73 cubic meters. So it's as simple as that. Just go through the example, do it yourself. You'll find that you should be able to find 2.73 if you do it correctly. Welcome to question number 6a. State the law of conservation of linear momentum. Remember, momentum is the product of mass and velocity of a body. Alright, so it's governed by a law which is popularly called or known as conservation of linear momentum. It states that the total linear momentum of a closed system remains constant both before and after collisions, provided no external forces act. So this one is just asking us to state the law of conservation of linear momentum. Explain the difference between elastic and inelastic collisions, again related to momentum. Alright. So in an elastic collision, both momentum and kinetic energy are conserved. Remember, this is a kind of momentum where bodies after collisions will separate. They don't stick together. So the total momentum and the total kinetic energy are conserved after collisions in an elastic collision. While in an inelastic collision, momentum is conserved, but kinetic energy is not. Some of it is lost as a heat, and also as sound and deformations. This is a situation where bodies collide and they tend to move together, but mass can change and other things, speed can also change, leading to a situation where kinetic energy is not conserved, although momentum is conserved. What is the use of cramp zone of a car in times of collision? The cramp zone is just the front part of the car, just the front of the car, around the bonnet where the engine is housed over there. That's called the cramp zone. It's a bit far away from the driver. So what is the use of the cramp zone of a car? I wish I brought a diagram of a cramp zone of a car showing the cramp zone. Alright, but basically the use of the cramp zone is to increase the time taken for the car to stop during collision. So this reduces the rate of change of momentum, hence lowering the impact force on passengers and preventing serious injuries. Welcome learners, this is Black Slides Online Secondary School. Question number 7. Why is an object moving at a uniform speed in a circular path of constant radius is said to be accelerating? When a body is moving along a circular path, we say that it is accelerating, although its speed, linear speed, is considered to be constant. So a body moving in a circular path is considered to be accelerating simply because velocity of the body, which is a vector, changes continuously in a circular path. It keeps changing. So velocity changing leads to an object accelerating. So we are saying its velocity changes continuously in a circular motion. So velocity change leads to acceleration. A giant wheel of radius 40 meters is rotating about the axis at a frequency of 5 Hz. Calculate the angular velocity in radians per second. Alright, so look for what you're given. You're only given the radius here and the frequency. So angular velocity is calculated using the formula. This omega, small omega, which looks like a W, angular velocity is equal to 2 pi multiplied by frequency. Thankfully, everything is given. And we have no business with the radius at the moment. So we don't need the radius there. This could have been important if we were asked to calculate the linear velocity. So it could be 2 pi RF. Okay, so just take 2 pi multiplied by the frequency, 2 pi multiplied by 5, which gives us 31.42. Please discover the equations for linear velocity. It's just 2 pi RF. What is missing here is the radius. If there is a radius there, then this could have been a linear velocity. The 8 figure below shows is a diagram of a type of logic gate. Alright, so I'm sure this is the logic gate. Consists of two switches which are in parallel. Identify the gate. This gate is called OR gate. It's an OR gate. Why? Because for current to flow, it's either A has to be closed or B has to be closed. So it's either A or B. So it's an OR gate. Draw the truth table for the logic gate. Alright, so in this case we have two inputs, close switch 1 or close switch B, close switch A or close switch B. So when both switches are open, like both of them are 0, 0. 0 means the switches are open, they're not closed. Right now they're open. So there's no current flowing through A, no current through B. So the bulb will not give light. But if we leave A open and close B, current will still pass through this path and light the lamp there. So the lamp will light. 1 means the lamp is going to light, to turn on. When we switch A is closed, even if B is open, the lamp will still give light. When both switches are closed, A and B closed, the bulb will give light. So there are 3 combinations that will allow the lamp to give us light. 3 marks. Question number 9. State any 2 similarities between a camera and a human eye. How is a camera similar to a human eye? The camera and the human eye has the following similarities. Both of them have a convex lens that focuses light to form an image. The lens in a camera is convex, just like the one in the human eye. Both are going to form real inverted images on a light-sensitive surface, the retina in the eye and a film in a camera. Both have aperture, an opening or diaphragm that controls how much light enters. And both adjust focus to form a clear image of objects at different distances. So welcome learners. An object of 2 centimeters high is placed 8 centimeters away from the converging lens of focal length 2 centimeters. Using lens formula, calculate the image distance and the magnification of the image formed. So recall the lens formula. The lens formula states that 1 over f is equal to 1 over u plus 1 over v, where f is focal length, u is the object distance, and v is the image distance. So we are asked to calculate the image distance to calculate this v. Alright. So all you have to do is make 1 over v the subject to yield this and substitute the given values. F is 2. F is 1, 8. What's this? Okay. So we are saying F, the focal length is 2 centimeters. Yes, put it to the substituting. And we are told that the focal length is let's read the question again. An object of 2 centimeters high, okay, we can leave that, is placed 8 centimeters away from the converging. So this is distance. Okay, so this is object distance, which is u, plus an 8 there, from the converging length of focal length 2. All right, so we have focal length is 1/2, where the object distance is 8. And simplifying and making V the subject to give us V equals to 2.67. All right, which is the value of the object distance, rather image distance. So to calculate magnification, recall that magnification is image distance divided by object distance. So the image distance is 3 divided by 8 divided by 3, which we got earlier on. This one here, divided by object distance, which is 8. So calculating will give us a magnification of 0.33. Welcome to question number 10. Figure below is a diagram of a pulley system being used to lift a 220 kg mass through a vertical height of 2 meters when an effort of 50 is used or applied. Okay, so using the setup, we are asked to calculate the efficiency of the machine. So for us to calculate efficiency, first of all, we must find the mechanical advantage of the machine. Remember, mechanical advantage is load divided by effort, and the load is 200. We're getting 200 from 20 times 10, which is basically the weight of the load, divided by 50, which is effort. So mechanical advantage is 4. So to find efficiency, we shall use the equation mechanical advantage over velocity ratio times 100%. So mechanical advantage is already found. It's this one here. The velocity ratio is just the number of sections of the string. So the string has 1, 2, 3, 4, 5. That's the velocity ratio of the machine. It's also equal to the number of pulleys. So take mechanical advantage divided by velocity ratio times 100. So this pulley system is 80% efficient. Work out, work input. So basically the work input is effort times distance moved. But for us to arrive at that, we need the following information. From the machine there, we have seen that the load is 200, is 20 kg times 10 newtons, and the velocity ratio is 5 because the rope has 5 sections. And mechanical advantage is what we just worked out. Well, efficiency is 80%. So work done on load is going to be 200 times 2. Remember, the 2 is how high the load is lifted. So the work done by the load is to 400 joules. And the distance moved by the effort is going to be 2 multiplied by 5, which is 10 meters. All right, the 5 is the number of sections through of the system there. Therefore, work done by effort, which is input work input, is going to be 50, which is effort, multiplied by 10, which is 500 joules. So go through the solution again until you're sure that this is what has to be done. In case you have questions, don't hesitate to reach us. We shall be glad to share with you the solution step by step. Welcome to number 11. Number 11 is about this figure here. Figure 4 is a diagram showing radiation passing through an electric field. So we have radiation, we have an electric field here between two plates. This plate is positive, this one is negative. So the electric field is between these two plates. So the radiation is passing through. Name the particles taking paths X, Y, and Z. Within an electric field. So in this case, X, you can figure out X must be alpha radiation. Alpha is deflected towards the negative plate. That means this is alpha, X is alpha, and this Z must be beta, and the Y must be gamma. Of course, gamma is not a particle, it's just radiation. So the question could have been polished up to say name the radiations rather than particles, because not all radiations are particulate in nature. All right, so X is alpha. How do we know that? The fact that it's deflected towards negative terminal gives us a hint that this must be positive, because unlike charges attract. So alpha is positive, will be attracted towards negative, and beta Z, it must be beta because it's negative, and negative is attracted to positive. And this Y, which is gamma, is neither positive nor negative. It's not a particle, it's just radiation. That's why it's not deflected either towards the positive plate or the negative plate. Explain why particle Z will deflect towards the positive plate of the electric field. So I've already explained that one. All right, so just to go through again, so we are saying beta is X is beta particle because it's negatively charged, so they are attracted towards the positive end. Gamma is uncharged, therefore it just goes undetected. And the alpha particles are positively charged, so they are attracted or deflected towards the negative plate. So explain why particle Z will deflect towards the positive end. We are saying that particle Z is beta particle radiation, which carries a negative charge, electric charge. Opposite charges attract. So because it's negative, it will be attracted to positive terminal on that side. Okay. When thorium-230 nucleus decays, it emits radiation and it changes into radium-226. So thorium undergoes a decay to form this. Complete the equation by filling in the box. Alright, so over here, it means we need an alpha particle. Of course, you can also present it in form of alpha particle. And alpha is something like this, yeah, with a mass of 4 and charge of 2. All right, so either this or that. How do we know that? This is so in order to, because we when you subtract the numbers, 230 divided by 226, the result is 4. And the 90 minus 88, the result is 2. So this represents a nucleus of helium. So this must be an alpha. So what type of radiation particle is emitted in thorium by thorium? In the equation above, reaction above, nuclear reaction above, so this must be alpha. It's alpha particle or alpha radiation. Figure below shows a detector of radiation. Okay, identify the instrument. This instrument is called diffusion chamber, or rather diffusion cloud chamber. Diffusion cloud chamber. This one. Make sure you know these things, including the others, such as the centration counter, the gold leaf electroscope, the GM tube, and the other means of detecting radiations. How does the instrument work? To measure presence of radiation. Alright, so for this to measure the presence of radiation, you see in here there's what is called solid dry ice. There's dry ice. The dry ice is basically frozen carbon dioxide. It's very cold. Its use is to bring about a cold environment inside it. So this is what will happen. The dry ice cools the chamber, creates a very cold environment. This will make the alcohol vapor. There's also alcohol vapor in here. There's vapor here, around here. The alcohol vapor inside to become saturated. All right, very dense. So when that happens, when radiation passes through, radiation comes from the source here. When the radiation passes through, it's going to ionize the air, the alcohol molecules along its path. Okay, so we are saying there's alcohol vapor here, which needs to be saturated by the solid dry ice, which is very cold. All right, so when it gets saturated, the radiation that passes through the vapor is going to ionize the alcohol. All right, so once ionized, the alcohol is going to condense, like to turn into liquid, and these ions forming tiny white clouds, which are called trails, that show the path of radiation. So these are the three things that you should have written in order to get all the 3 marks there. Welcome to question number 12. Describe an experiment that can be done in order to calibrate spring balance. Remember, spring balance measures weight of bodies or objects. All right, so if it doesn't have a scale on it, it means it's not usable. You can't use it. So to get it usable, you must calibrate it, have it calibrated. So the steps to calibrate it include the following. So first and foremost, you fix the spring balance vertically to a frame support. So it's like you hang it. You can use a clamp stand so that it is firmly held vertically. Then check and adjust the pointer so that it reads 0 with no load. So the pointer must be on the 0 mark. Mind you, there is no scale at the moment, so we're trying to get a scale placed on it. Okay, so check and adjust the pointer so that it reads 0 with no load on it. And then gather a set of standard known masses. Okay, you can have 10, 20, 30, 40 grams. Right, then you calculate each of the masses. Calculate the weight of each of the masses. How do you do that? You convert the weight, you convert the mass into newtons. All right. Remember that 1 newton is equal to 100 grams. So use that conversion factor to produce the weight in newtons. Then hang the masses, the first mass, gently on the hook of the spring balance. Right, and allow the spring to stop moving before you take a reading. So allow the spring to stop moving before taking a reading. Alright, so and then mark the pointer position with its correct weight value. Mark the pointer position with its correct weight value. The weight that has brought the pointer at that point. So mark the pointer position on the scale panel. All right. Then remove the mass and repeat for every other mass that you have. Let's say you have 10, 20 grams, 30 grams, 40 grams, 50, and so on. Also, you repeat the process with every other mass. Check the readings when removing masses to confirm accuracy. Check the readings when you are removing the masses to confirm the accuracy. Alright, and lastly, add equal divisions. So you mark on the scale panel, you add equal divisions between marks to finish the scale. In so doing, you are said to have calibrated, and now you can go ahead to use it to measure weight. Describe an experiment that could be conducted to determine acceleration due to gravity in an area. In other words, describe an experiment that you can do to calculate the value of G. So the description takes the following pattern. So you tie a small bob, a small mass, to a thin light string to produce a pendulum. Then clamp the string firmly to a stand so it swings freely. Measure and record the length of the string of the pendulum from the support to the bob center. Displace or push the bob slightly and let it swing through a small angle only. Use a stopwatch to measure the time taken to make 20 complete oscillations. Then calculate the period. Remember, period is simply the time taken to make one complete oscillation. You take the time taken to complete 20 oscillations, divide by 20. That will give you periodic time. So repeat the steps for at least 5 different lengths of the pendulum. Alright, so for each set, calculate period and record all values in a table. Then you plot a graph of the square of the period against length, and you draw a line through the origin. So the gradient of the graph is going to give us the value of G. So that's how you will determine the value of G in a particular place. Thank you very much, learners. It has been quite a long session to revise this paper. As always, if you are left behind, simply send me a text message. I'll be glad to rectify what I might miss. See you in the next lesson. Bye bye.